Okay, so now we're ready to prepare for the test I described earlier. To remind you what it is, I'm going to try to answer the question, could a neural network learn mathematics well enough to pass the Regents exam in geometry in a human-like way from human-like input? So first, let me describe the tenets of the approach that I am going to take to addressing this question. The first tenet is the idea I've already described, that mathematics offers culturally constructed model systems that support reasoning in number, geometry, and many other domains. Some characteristics of these systems are implicit in everyday experience interacting with objects in the physical world. But others arise from structured interactions with physical instantiation of these culturally constructed models, or with symbols that are grounded in such models and that are guided by peers, caregivers, and teachers. This guidance is generally sensitive to the capabilities of the learner and combines demonstration, explanation, practice, encouragement, and testing with feedback. And the final tenet is that neural networks have many of the right characteristics to capture how humans acquire and understand these culturally constructed models, but they're going to need to be extended beyond their current capabilities to fully succeed in this way. So here's the project that I'm envisioning. We'll create an artificial world and a simulated learning agent. And this part of the approach is inspired by the DeepMind Atari project that was described in a recent publication by Vladimir Mny et al. In this project, Vlad and his collaborators created an artificial agent that received the very same input a human would get from a computer screen, based on a large suite of games that were created back in the 80s by the Atari company. These are simple action games, which are played by manipulating either a joystick or pressing keys. So the input is a bitmap, like the screen of a computer, and the output is the set of possible actions that can be taken by the player of the game. And the model is a deep neural network, as shown here. The training in the model is governed by learning to predict which action will produce the greatest expected reward based on the observed point scores that are produced by the actions that the agent takes. At first, the agent's actions are completely random in this space, but gradually it acquires experience with those actions that produce rewards and those actions that don't. And over many, many repeated trials, acquires the ability to play these games, many of them at a way that exceeds or certainly matches human-like abilities with these kinds of games. So our agent will be a similar kind of simulated agent that lives in a similar kind of artificial world with a bitmap input and a restricted range of actions for its output. We'll let this agent explore its world and learn through structured experience guided by supportive teachers. So in a way, these video games are supportive teachers because they change as the agent plays. They become harder and harder. And they provide this series of experience that guides development. In a similar way, we'll think of teachers and others supplying experience that guide learning. We'll allow the agent to acquire intuitions and skills related to number, measurement, algebra, and geometry, and gradually build toward multi-step reasoning and problem solving under continued structured guidance, such as children do receive in school. So let me describe some of the parts of this project. First, the artificial world. I envision a large two-dimensional planar surface where flat objects can be placed or on which drawings can be made, either by the agent or by its teachers. So, for example, this could be a display that could be presented to the agent. And there would also be a symbolic communication channel, like a teletype. That is to say, we won't solve the problem of perceiving and understanding spoken language, but we'll assume that the agent will receive typed inputs from a teacher and be able to produce typed outputs as responses, similar to what happens in the Turing test. The teacher can give instructions and ask questions in words or can present mathematical expressions, and the agent can reply with words or mathematical expressions. So, for example, the teacher could say to the agent, "Can you touch the red triangle?" And the agent could then move and touch it. The agent will have a head with a fixed eye and a simplified hand. It'll be able to move its head to fixate anywhere on the plane, and it will be able to move its hand to touch, drag, rotate, or flip objects that are placed on the plane, and also to manipulate tools so it can draw, copy, and measure objects. And I'll say a bit more about that. The agent will also, of course, read and write linguistic and symbolic expressions as character strings on the TTY. So let me share with you some of our initial thoughts about learning for the simple agent. Learning will be exploration, reinforcement, correction, and imitation driven. And this is a little different from the Atari DeepMind project because in their initial work, they focused on the idea that all of the learning could arise through learning whether you get points for your actions. I believe that that is certainly an important part of learning, but it's not all there is to learning. And part of learning involves exploration. The agent needs to be motivated to explore, and that can be studied within the context of reinforcement learning if one envisions the notion that there may be intrinsic reward for discovering new things or mastery of things that are presented in the environment. Exactly how those reward functions are implemented is an important part of the project. The agent will also be able to benefit from observing correction. So not only right or wrong information, but this is how you do it information, and will be able to learn from imitation as well as essentially error correction. As one specific concrete example of something that I think will be important for the agent, I'd like to just briefly mention how it might be able to learn invariant shape representations through exploration of its environment. This is strongly influenced by Jeff Hinton's proposal of a transforming autoencoder as a mechanism for learning an invariant representation of shape. So here's the basic idea. Imagine the agent is fixated at a particular location in its two-dimensional world, as indicated by the position of the eye in the diagram. And there's a triangle at a certain location away from its point of fixation. Now, the idea of the transforming autoencoder is to take the image as it exists, that is to say, located up and to the right of in the visual field, together with an eye movement plan, in this case, move my eye up and to the right, to predict what the next image will look like. This is implemented by essentially having both the current image and the eye movement plan be inputs to a hidden layer, which is then used to predict what the next image would be. Now, the eye movement could then occur, producing the actual next image, which would then be the teaching signal to train this network. In this way, the network would be able to learn what a shape will look like when I fixate it, and that representation would be an invariant representation of the object's shape. Now that, of course, is an insight that Hinton captured with his transforming autoencoder, and is one of the things that I think will provide a foundation for general purpose, generalizable learning. Wherever an object appears in the world, if we fixate it, it comes into a canonical form on our retina, at least up to rotation and scale. And if we can anticipate what it looks like, we don't even have to fixate it in order to generate such a representation. The model can also learn separate representations of objects and of transformations. In fact, one can imagine learning the eye movement plan that brings the object into the center of fixation, and in that way, we're learning what those transformations are that are needed to create, let's say, correspondence of one shape with another. This idea should be extendable to capture the effects of translation and rotation carried out not only by the eye, but also by the hand. So if I know what will happen to an image if I move my eye to it, I could also imagine learning what would happen to my image of an object if I touched it and rotated it by a certain amount. Maybe that way I could learn about the effects of rotations on objects and how to bring them into canonical positions as a result of my actions in the world. I could then imagine these activities and create an internal representation, similar to what we saw in the shepherd proof earlier. Another important aspect of my thinking about learning in the model is that it will be curriculum-based. That is to say, the teacher will set tasks at the edge of the competence of the learner, demonstrating, observing, correcting, and reinforcing the learner for its behavior. The task will be set using linguistic or symbolic inputs along with virtual objects and diagrams that the teacher can place in the environment. And finally, explanation and justification will be part of what it is that has to be learned. According to the underlying idea I have about this, justification and explanation is not necessarily the basis on which we can perform correctly, but it is part of what we are expected to be able to, it's part of what we are expected to know, why our actions are valid. And my view is that this kind of thing ought to be learnable in just the same way that learning to do the right thing should be learnable. Learning to give the right explanation should be learnable as well. So an early curriculum for teaching the agent will involve sensory motor interaction with shapes. The agent will be able to move and zoom its viewpoint to achieve translational and scale invariance. As we've already seen to some extent, it'll be able to grasp and move objects to the center of its field of view. It'll be able to rotate, translate, and fit objects to fit shapes or cutouts in the plane. So I imagine, for example, that one of the tasks that we could give the agent would be to reach out, touch the solid object, and drag and rotate it so that it comes into correspondence with one of the outline shapes at the bottom of the figure. And when it succeeds in matching one of those outline shapes properly, it would be just as though a kid had dropped an object through a slot in a shape sorter. Somehow children find that intrinsically rewarding, so we might imagine the agent would receive reward for achieving such an outcome. In addition, we could imagine the agent would learn to recognize and identify shapes through agent-teacher interactions. So, for example, the teacher might say, "What kind of a shape is the red one?" The agent might say, "Triangle." The teacher might say, "That's right, eh?" And from that, the agent could learn. So there are two key issues I see for the agent here. One of them is mastering structured sequential behavior. Neural networks work well for one-step computations. So when Siri interprets your speech, it's passing a representation of these speech sounds forward through a multi-layer neural network. That's basically a one-step computation. Can neural networks learn to produce a structured sequence of actions? Well, in a way, the video game player, the Atari video game player, is performing a sequence of actions, but it may not be sufficiently structured. And one of the key issues that we're exploring is how to get enough structure into the sequential behavior of our agent. Second question is generalization and abstraction. Neural networks rely on similarity-based generalization. Will this allow them to acquire skills that they can apply generally without exhaustive experience in a way that captures, the degree to which our mathematical skills are fully generalizable? That is another key question that we'll be exploring in this work. I'd like to illustrate some of the themes with a simple task, not quite at the level of geometry, but one that is part of mathematical cognition, an early part, I would say, and that is the ability to count objects, such as the display of objects we see here. A could watch T count objects, touching each one sequentially from left to right, learning to anticipate the next item T will touch and the next word T will produce. So the agent might see the teacher's hand moving through the array, starting with the leftmost object and saying 1, then the second one saying 2, and so on. And then ending by saying 6. There's 6 objects there. A could then attempt to replicate T's behavior, receiving a combination of kinds of feedback from T. If the agent starts at the left and moves its eye and hand to each successive object, T could observe if A is following the correct procedure. This could guide feedback, external control, and further demonstration by the teacher. So this externalization of the agent's behavior into a space that's shared between the agent and the teacher provides a mechanism, as Ali Bali and DeRusso discussed, whereby not only the outcome, but the detailed steps of the process that the agent engaged in can be observed by the teacher and subject to feedback and adjustment and correction. Regarding the question of generalization, successive fixation provides a natural basis for generalization of action. So, for example, in counting, the current object on this view is always at fixation. And if there's another object to the right, then we should continue on to count it. And this will be true regardless of which object we're currently fixating on. When we get to the end, the absence of additional objects provides the stopping condition. So, very simple set of production rules, if you like, would allow an agent to step from left to right through this series of objects and to stop at the end. Those would be very general ones because at each point we'd be reusing the very same connections. That's afforded by the fact that we change our point of focus as we move through the display. It's also reminiscent of the operation of a Turing machine. In this case, though, the external world is like the tape of the Turing machine. And of course, the external world is like that tape in the sense that there's no particular limit on the number, let's say, of objects that we could place before a child to count. Where does structured action come from? Structure emerges from culturally defined components that can be assembled, we're arguing. So I can illustrate this by a simple way of thinking about addition, which we can think of as consisting of the assembly of subtasks, which we know kids actually master because actually they've been assessed many times by psychologists. We can think of addition, for example, as two give ends and one how many. So suppose the teacher says, how many is 2 plus 3? Well, the agent could be taught to answer this question according to the following procedure. It could first extract from its stack of objects 2 objects. I showed that abruptly, but you could imagine 2 steps, 1, 2, and the teacher could say, uh-huh. Then it could extract 3 objects and say 1, 2, 3 as it went. So performing a give-end task now with 3 instead of 2 objects, and the teacher could say, okay. And then it could count all the objects. 1, 2, 3, 4, 5, and stop and say 5. And the teacher could then say, great job, eh? Now this procedure is actually described as the procedure that children are taught to use, were taught to use at the Carnegie Mellon Preschool back in the late 1980s in a book by Siegler and Jenkins. And it illustrates the culturally defined structure that may be available from the environment to provide the structure that organizes action. So part of our thinking is that the emergence of structure arises from these culturally defined components that are conveyed by structured teaching environments. So maybe you think that we'd be able to build a model that could learn how to count and add small numbers. But you may not be convinced yet that we'll be able to scale up to geometry. And indeed, Jeff Hinton said to me not that long ago that perhaps this is too hard a task for a neural network, even if I'm giving myself 10 years to solve the problem. I admit that it's going to be a daunting challenge, but let me tell you about some of the thoughts we've had about how we're going to move in that direction. We're going to provide the agent with the opportunity to learn how to construct, measure, copy, scale, and establish relationships between objects by giving it, in addition to objects in the world, some tools that it can manipulate. We've actually created this virtual world, again inspired by the Atari game project. There's a computer program that we have now that produces images just like what you're seeing here on the screen of a computer so that a human being can interact with these objects. And one of the objects in this environment is a ruler, which has a red dot at one end and a green dot at the other end. If you touch the red end, you can drag it. If you touch the green end, you can extend it or reduce its length if you go in and out, or you can rotate it when the red end will stay fixed. You can also draw with this ruler. If you go into draw mode, you can draw a line through the middle of the ruler from the red dot to the green dot, or you can rotate the green end and draw an arc or a circle with the ruler. With these tools, we should be able to teach the agent to copy a given figure, draw a figure to specification, such as draw a triangle with sides of length 2, 4, and 7. Well, maybe that triangle doesn't exist. Or reproduce a figure at a different scale. Or maybe measure the lengths and angles of a given figure, assess parallelism of lines in a figure, assess similarity and congruence of given figures. And we should be able also to teach the agent to use the Cartesian coordinate system when given axes, a unit, and an origin. The ruler, as you can see, provides units. It doesn't explicitly provide an origin, but of course, we could provide a point on the plane, and we could mark the grid on the plane instead of the ruler to provide a coordinate system. And again, this would provide a framework within which we could teach the agent to do such things as place a point at the position x equals 4 and y equals 3 on the plane. Building on that, we hope to move towards teaching the agent advanced topics in geometry. So to carry out Euclidean constructions, constructing a perpendicular to a given segment, constructing triangles and other shapes from a variety of alternative different kinds of specifications, determining the perimeter and area of polygons and circles in given units, establishing correspondence between figures given information about shared properties, and solving geometry problems requiring intermediate inferences and computations. The problem that I showed you early on in the talk does require intermediate inferences and computations, and ultimately the goal is to be able to solve problems of that type, laying out intermediate results in algebraic expressions. For some problems on the test, actually providing justification based on learned knowledge of appropriate justification steps, and even, ultimately, to assess the provability of some stated relationship. So those are the long-term goals for the project. Is it possible? I don't know. There are clearly many gaps to fill. I do think some of what I've proposed is doable, so I'm optimistic that we'll at least make some degree of progress. For example, the Google DeepMind team has already developed a version of their simulated agent that can move its simulated point of fixation and read off successive characters in, let's say, the character string that labels the building number of a building in a photograph, or the series of letters and digits on a license plate in a sequential way, one by one, in a way that's very similar to what we envision for some of the early stages of learning in our agent. So I think at least the early stages are well within the range of what will be possible in the next few years, and we're already beginning to pursue some of the work on counting and related topics within a neural network framework. To me, there are two big gaps. The first is we haven't really begun to address learning to manipulate mathematical expressions rather than, let's say, learning to manipulate objects themselves. And manipulating mathematical expressions while representing what they mean, according to Needham, is, the essence of actually using the notation system in this way of manipulating the objects themselves through interaction with the symbols that stand for them, as opposed to just manipulating the symbols by themselves. And that is really the essence of what we'd ultimately like to accomplish. We also have not begun to address anything related to explanation, justification, and formulation of proof. I think that is a big gap as it stands. But since proof and justification are major challenges for humans as well, as Berger and Shaughnessy's work suggested, it makes sense to leave this as the final challenge for the agent. Whether we succeed or not, my feeling is we'll learn a lot along the way. We'll learn new ways of understanding where structure comes from in mathematical reasoning. We'll learn new ways of teaching neural networks. We'll achieve a deeper understanding of how teachers shape the behavior of learners. And we'll learn new ways of thinking about what it means to be able to think mathematically. So I don't know if we'll succeed, but I hope you will wish me luck in this effort, and I thank you very much for listening.